Okay, let's unpack this. Have you ever looked at something like a deficit to the power of math and just wondered what's really going on? Like, what are the rules?
Yeah, definitely. And that's exactly what this material we've got here dives into. It's all about indices or,
Yeah,
exponents. It's
exponent.
basically the rules for when you multiply the same number by itself over and over.
So our mission for this deep dive is to just pull out the key stuff, right? Give you a quick handle on this whole concept from these sources.
Exactly, a shortcut to understanding.
So what is this to the power of may thing, really? How does the source define it?
Well, it defines amin simply as a short way to write multiplying a that's the base by itself m times. So m is the index or the exponent.
Okay, so instead of writing out, say, $2 2 times 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 $2, that's 7 times.
You just write $27.07. Much neater.
Yeah, way neater. It's just about making repetition less, well, repetitive.
Precisely. And what's really cool is how these things interact. There are these simple laws that govern them. The material lays out a few core ones.
Okay, let's get into those. What's the first big one, like when you're multiplying?
Right. So the first is the product law. It says if you're multiplying powers and they have the same base, a, you just add the exponent.
Add them?
Yeah, the rule is 1 times an am plus min d.
Okay, hold on. So if I had like 7 times A41, that's not a $28.
Oh, no, simple addition. It's a dollars plus 4 5, which is just a lever.
Got it. Okay, that's straightforward enough. What about division then?
That follows logically. It's the quotient law. Same base again, but this time you divide, like fracking.
You subtract.
You subtract the exponents.
Yeah,
Fracton.
oh, okay. So using the same numbers, frac A4 would be a 7 basal, which is 304.
Exactly. You're basically canceling out common factors.
Right. That makes sense visually, too.
Yeah.
Okay, and the source mentions a third main one.
Yeah, the power law. This is when you take a power, like a male, and raise that whole thing to another power. And so it looks like mm.
Oh, like a power of a power? What happens then?
You multiply the exponents. So mn, the source example, A344, becomes A3 times 4.
Which is a $12.
Yeah.
Okay, multiply those two. Got it.
And, here's where it gets really interesting. These rules, they work even for exponents that aren't like positive whole numbers.
No. And like what? 0? What does the source say about something to the power of 0? That feels odd.
It does seem counterintuitive, doesn't it? But it actually comes straight from the quotient law. Think about fracimam.
Okay, well, anything divided by itself is 1, right? Assuming A isn't 0.
Exactly. But using the quotient law, fracimam is also a rem, which is $t.
Ah, so $2 has to equal 1 for the rules to be consistent.
Precisely. So yeah, $50 is 1 over dollars, $2 is 1. Anything non-zero to the power 0 is 1. It fits the system.
Wow. Okay, that's clever. What about negative exponents then? Do they fit too?
They do. Same logic, really.
Right.
Think about frac. We know $t is 1 minus a, so that's frac of 1.
Right.
But using the quotient law again, frac n is a dollar, which is a dollar.
So A must be the same as frac A. A.
You got it. A negative exponent just means take the reciprocal of the positive version. So A3 is just frac n of 2.
Okay, it's like it flips its position in a fraction. That actually makes a lot of sense now, seeing how it connects.
Yeah, it's quite elegant how it all ties together.
Mm.
The source also touches on fractional exponents.
Like a half or a third. What do those mean?
They represent roots, so a means the ninth root of a.
Oh, so a 12 is just the square root of a.
Exactly. And a 13 is the cube root.
Yeah.
And then something like a combines them. It's the ninth root of a12.
Okay, so roots aren't some separate thing. They're just powers, too, just fractional ones.
Right. It unifies the concepts.
So pulling it all together, what's the payoff for understanding these rules?
Well, the big thing in material shows is simplification. You could take really messy-looking expressions with lots of powers and boil them down using these laws.
Makes them manageable.
Definitely. And it also shows how you can use these rules to solve equations where the unknown, the x you're looking for, is actually in the exponent.
Oh, right. Like $2x equals 80i? You need these rules to figure that out easily.
Exactly. You'd rewrite 8 as 2, 3, 3, 3, and then, $6 must be 3. These laws are the key.
So these few core laws of indices are, well, they're pretty powerful tools then for cutting through complexity.
Absolutely. They're fundamental building blocks in algebra and beyond.
And maybe connecting this outwards, really getting why these rules work, especially the weird ones like ln or the negative ones. Perhaps that deeper understanding is what really unlocks your ability to tackle much more complex math or science later on, where these exponents just show up everywhere, something to think about maybe.